Welcome to the next part on our unit on electric charge and electric field. In this part, we're going to be doing some basic examples of electric field calculations. So to begin with, we're going to start with a basic point charge. So in this case, the source of our electric field is a plus 3 Coulomb charge. And we want to know the magnitude and direction of the electric field 0.25 meters away. Now, 0.25 meters away forms a circle around our point charge. And what we know is that anywhere on that circle, the electric field is going to point. I don't know why I drew a circle there, so let's get rid of that. Oh, now my eraser is working. Who knew? Anywhere on this circle, the electric field will point outward. So the direction is radially outward from the plus 3 Coulomb charge. So put that in as our first answer, radially outward. Now we need to figure out how big is it anywhere on that circle. And we do that calculation using K times Q divided by r squared. So that's 9 times 10 to the 9th Newton meters squared per Coulomb squared. And let me clean that up. Our source charge in this case is 3 coulombs, and our distance is 0.25 meters, so we have to square that. And that works out to be 4.32 times 10 to the 11th, and the units here are newtons per coulomb. You can see those units as an aside if we go back to F equals QE. Force is in newtons, charge is in coulombs, so electric field has to be in newtons per coulomb so that the units on both sides of the equation work out. Not this unit so much, but next unit you may also see an alternate set of units for the electric field. And I'm just going to write those up here because you may see them. 1 Newton per coulomb is equivalent to 1 volt per meter. Okay, so now back to the example at hand. The electric field has a magnitude of 4.32 times 10 to the 11th newtons per coulomb and points radially outward. Now, what if the charge causing the electric field in the previous question was negative? Well, if I had a negative 3 Coulomb charge and I look 0.25 meters away, now the electric field everywhere will point inward. So the direction changes, but the magnitude doesn't. And you can see that if we go back to E equals K times the absolute value of Q divided by R squared, that's again going to be 9 times 10 to the 9th Newton meters squared per Coulomb squared times 3 coulombs divided by 0.25 meters squared, which is the exact same number we just calculated. So if the charge were negative instead of positive, the direction is inward, but the magnitude is the same. For our next example, we're going to look at 2 positive plus 2 coulombs separated by 3 meters. So here is one of them, plus 2 coulomb. Here's another, plus 2 coulomb. The total distance between them is 3 meters, but in this problem we are looking at the halfway point. So this is 1.5 meters and this is 1.5 meters. Let's think about directions first. So I'm going to call the one on the left A and the one on the right B. So if I draw the free body diagram of a little positive charge positioned here, the electric field or the force from B would be to the left because it is repulsive. From A, it would be to the right because that is also repulsive. And because that's the direction of those two forces, that means that the field from charge A will point to the right, and the field from charge B would also would point to the left, like the force from charge B pointed to the left. Now you can probably see where this is going already, but just to put it all in place, the field from charge A is going to be K times 2 coulombs divided by 1.5 meters squared, which has a value of 8 times 10 to the 9th newtons per coulomb. And from charge B, it's K times 2 coulombs divided again by 1.5 meters squared, which is also 8 times 10 to the 9th newtons per coulomb. And now I can write the total field. It's going to be the field from A plus the field from B. And notice I've written this in vector form, so I haven't thought about direction yet. But when I do that, because it is vectors, I do need to define a positive direction. So let's let positive be to the right. So that means EA will be positive 8 times 10 to the 9th newtons per coulomb, and EB will be negative 8 times 10 to the 9th newtons per coulomb. And that sums to 0, and we get at the point right between our two charges that the total electric field is 0. Okay. So how would the answer to the previous question change if the charges were negative? It wouldn't. What would change? There would be subtle differences along the way during the process. So EA would still equal EB, which would still equal 8 times 10 to the 9th newtons per coulomb. I did remember that number correctly, yes. The directions would be different for the individual field pieces. So EA would now be to the left and EB would be to the right. Am I thinking about that right? Yeah, that's right. So if this were a negative 2 coulomb and that were negative 2 coulomb and I put a little positive charge here, then it would be attracted. So it should be EA to the left, EB to the right. But since they're still in the opposite direction and the magnitudes didn't change, when I calculate E total equaling EA plus EB, I still get an answer of 0. Okay, so now let's think about what happens when I have like charges, but they're not the same size. So now I have a negative 1 coulomb and a negative 2 coulomb separated by 1 meter. Okay, so here is my negative 1 coulomb. Here is my negative 2 coulomb, and I know the total distance between them is 1 meter. And what I want to find is at what position does the electric field go to 0? Now, what I know is that because they have the same sign, that the electric field will go to 0 somewhere between them, because that's where the piece from the negative 1 coulomb and the piece from the negative 2 coulomb are in opposite directions. So I'm going to define a spot somewhere in between these two. That's what I want to know. And I'm going to let the distance from the negative 1 coulomb be x, which means the distance from the negative 2 coulomb to that same spot has to be 1 minus x. just again, in between the direction of the field from the two pieces will be opposite. The field due to the -2 will point to the right because a positive charge would be attracted. Same thing for the -1, except it points to the left. And I want to find the point where these two are equal. So I've defined an arbitrary position x where I'm going to do my electric field calculation. I'm going to begin by finding the individual pieces. So the field due to the -1 is going to be kq divided by x squared. So that's 9 times 10 to the 9th Newton meter squared per Coulomb squared times 1 Coulomb divided by x squared. Oh, and I forgot my absolute value sign there. There it is. And the field due to the -2 will be kq divided by 1 minus x, the whole thing squared, because that's where my arbitrary position is away from the -2 Coulomb charge. So plugging in. There we go. And now I'm going to define total field at the position I'm looking for equals 0. And that has to equal E -1 plus E -2. On the previous slide, I did not define a positive direction. I should have. So let's go back and let to the right be positive, which means when I go here, I'm going to let E -1 be negative. So it's going to be 9 times 10 to the 9th Newton meter squared per Coulomb squared times 1 Coulomb divided by x squared with a negative sign out front showing its direction, plus 9 times 10 to the 9th Newton meter squared per Coulomb squared times 2 coulombs, all divided by 1 minus x, whole thing squared, and that has to equal 0 newtons per coulomb. Okay, couple things to notice is I have a 9 times 10 to the 9th in both terms, and that equals 0, which means I can cancel it. Essentially, I'm dividing out the k. It doesn't matter. The next thing I need to do is find a common denominator. So my common denominator is going to be x squared times 1 minus x squared. And then when I put everything over the common denominator, I need to multiply the first term by 1 minus x squared. So I have minus 1 minus x squared times 1 Coulomb, plus on this side, I need to multiply by the other part of my common denominator. So that would be x squared times 2 Coulomb, and that still has to equal 0 newtons per Coulomb. For this statement to be true, the numerator of it must equal 0. So I can drop my denominator at this point. So I'm also going to drop the units of coulombs. Actually, I'm going to drop all of the units to make life a little bit easier. Our distance, if we kept the units properly, which we haven't because we divided out the Newton meter squared per Coulomb squared up here and didn't adjust the units to the 0. So let's actually just scrub them completely. There we go. Getting rid of units. There we go. Okay, so -1 minus x, the quantity squared, times 1, doesn't do anything, so I'm not going to write it, plus 2x squared must equal 0 in order for this statement to be true. Okay. Multiplying the parentheses out, that gives me -1 minus plus 2x minus x squared plus 2x squared has to equal 0. Or in other words, x squared plus 2x minus 1 has to equal 0. And if we put this into the quadratic formula, so we're going to come over here and quadratic formula it up, we get two answers. We get x equaling 0.41 meters or x equaling negative 2.41 meters. And this is the positive root, and this one is the negative root. This is the correct answer. This one has meaning, and I don't remember if I have another slide here. I do not. So I'm going to click continue here and go back. So let's talk about that negative 2.41 meter answer. Okay. That answer is for a slightly different but related question. Okay. If I have a negative 1 coulomb charge, and instead of it being a negative 2, if this were a positive 2 coulomb charge, if I come look over here, I would have the field due to the negative 1 pointing in, and the field due to the positive 2 pointing out. And so there would be a point over here to the left of the negative 1 coulomb charge where potentially you could get the field equal to 0. That number of negative 2.41 meters is that location where the field goes to 0 if instead of having like charges, we had mismatched charges. Okay, that does conclude this section. We have one more section to go where we will do further calculations of electric field.